quality GPS sensors to be used locally. And this work will be carried out in collaboration with Measuron. This is how the shape acceleration sensor looks like. It's a MEMS-based sensor, and it provides vibration and also 3D deformation. It's a very robust, sturdy sensor. This is a case study where it's used on a highway monitoring. Apparently there was some landslide expected along the highway in Minnesota, and Measuron instrumented along the highway the shape acceleration array and collected data. So this is the data that they've collected. They have seen this acceleration in the horizontal deformation, and at this point the landslide occurred. But around here, when the acceleration, they've seen the acceleration, the transportation agency was able to divert the traffic and prevent catastrophe. So now, of course, the plan is to add the pore pressure sensor onto this array. And another task involves developing a duty on the GPS sensors at low cost with high resolution. Now, health assessment team is led by Professor Guy, and Dr. Alan Marr is also involved. And of course, the objective is to integrate all the information from the sensory data and provide a health assessment both at the global and local level. And also, this information should be simple and reliable, and will be an aid to public safety professionals. So, in a nutshell, we are going to do some health monitoring at a global scale using interferometric and polarimetric SAR measurements. There will be a calibrated baseline for it. The a priori engineering knowledge and site information will be included into this health assessment. And once the vulnerable regions are identified, the area will be instrumented by shape acceleration for pressure and GPS sensors, and local health assessment will be performed. And this will be, I think, includes risk analysis and vulnerability analysis, and it will be done within a nation. All right, so in conclusion, we have exciting research at the right time. My background is not in civil engineering. I work on radar, but it looks like unrelated technologies came together to generate, to address an important problem. And we feel that there is a strong need for fusion of multiple sensory data, data collection at multiple scales, spatially and temporally, and also computational knowledge of Levees and use of a priori information, and integration of all this information into a form that is reliable and simple, that will be provided to the final decision makers is important. And of course, the framework that we are developing and technologies applicable to other areas such as transportation monitoring. That's all.
I must say that we as a company were very pleased to win the NIST contract together with RPI, but I had to have second thoughts when they presented me with a joint venture agreement in which I agreed to be responsible for the output of a bunch of researchers at RPI. If you want a sobering moment, think about that. But we have great partners in an exciting research endeavor here. I did want to try to look at it from a pragmatic, practical standpoint. That's where I spend my life now. We monitor sensors all over the U.S., thousands of them every day. And I want to run down through these things that she listed briefly and just tell you a little bit about how I see them from a practitioner, owner, user standpoint. The satellite imagery is really encouraging and promising. The people in space have done a lot of stuff on this, and NASA and stuff. This is the kind of stuff needs to drift into civil engineering, and we've got to find some ways to fund and support that effort. The challenge there is transforming enormous amounts of data into something simple that non-technical people can understand. Increasingly in the civil engineering world, we have non-engineers, non-scientists, non-specialists who are sitting watching this data and making decisions. So what we provide them must be simple, understandable, and highly reliable. With the satellite imagery, system reliability is one that we've got to work a lot on to get it improved. If we're relying on it, we can't suddenly have a satellite drop out of the picture, so that's a challenge for us. The other challenge, she mentioned 4 to 8 days on coverage. We need to figure out a way to reduce that if we're going to use satellites as a true real-time monitoring system to give us alerts and warnings. Civil engineering structures go from great behavior, everything looks okay, to a collapse within a matter of minutes. So if I'm only getting a passage every 8 days, I have to question how valuable that information is for real-time monitoring from a risk management standpoint. I kind of look at this as a high-impact, moderate-risk project. The technology's all done. It's been done for a long time. Our challenge now is to how to put it to work so that it really works in a civil engineering application. The GPS, again, by experience, a very useful sensor. Believe it or not, we're getting resolutions, precisions of about plus or minus 1 millimeter. That's absolutely incredible that I can go from a satellite to that kind of repeatability. A lot of people don't believe that because they say, well, look, my GPS here is lucky to tell me I'm within 50 feet. Well, we use differential GPS, in which you time from a reference station to a sensor, and you can get this kind of reliability. The challenge there is to get the cost down. The current in-place cost for a GPS system or a sensor is around $10,000. Now, you go buy the thing and they'll tell you 3 or 4 or 5, but that's bare. That doesn't include sensor, power supplies, communications, etc. One of the aims of this I set for this team to try to do was get that cost down to a target level of $1,000, a tenfold decrease. If they can deliver that to me, I can have all kinds of applications of that particular technology. So I judge this as a high impact effort on the part of the team with moderate risk. It's really, again, not developing new hardware gadgets and technology. It's packaging what we have, developing smarter software routines to transfer the data. Quickly to point sensors, she described one like the measurand equipment. I just forgot the acronym for a moment. Shaper accelerometer, thank you. There are many kinds of these kinds of sensors, and when we're developing more all the time, or researchers are, but when we start talking about infrastructure applications, we've got to keep in mind about 5 things. We've got to have high reliability. We've got to have long life. We've got to have low power requirements. We have to have wireless communications. And increasingly, we must think about them as how do we replace them. If we're going to do a smart building for the life of the structure, you're talking 75 plus years. Can you imagine having the responsibility for putting a strain gauge out on a structure in a severe environment and guaranteeing it's going to work 75 years? That's pretty darn tough. So we've got to think about how we replace these things if we're going to really monitor the structure through its life. These 5 things, however, are not very sexy research topics. And so there's the problem we have. However, they're very essential to get broader applications of what we're talking about here today. I think this is a high impact, intermediate risk type of endeavor we're under. The model updating, again, is very interesting. Being an old finite element person, how do I take measurements and back through the stiffness matrix to tell me what the loads were in effect, and how do I then do that a number of times to minimize error? Challenging. Imagine trying to solve that problem with so many unknowns. Lack of constraints. It's a real challenging problem. I think that's a long-term project, high risk, but a high potential payout. A couple more comments, and am I okay?
A couple more comments.
Okay. The university practitioner partnerships are particularly important in civil engineering to get research into practice. However, I think we've got to figure out how to shorten the time it takes to do this. I'm just today implementing some of the stuff I worked on at MIT in the 70s. That's a big challenge, and we got to figure that out. I think on this instrumentation area that we're talking about today too, we've got to really change our selling approach. It really is not working very well for us to talk about smart structures, in my view. That's a great topic to talk about in the university and to have very good discussions over lots of alcohol. But people aren't buying that. What they're buying, and we have to look at it carefully, what they're buying is things that produce value to them, they can translate into dollars, or things that help them manage and reduce risk, which also eventually translates to dollars. Those are the hot topics these days, along with asset management. So I think what we're doing translates a lot into those areas. I'll give you one more example. We have another research project with Louisiana Office of Coastal Protection and Research to develop an intelligent levee program. That's literally to take some of these kinds of sensors, put them in 100 miles of levee, and be able to predict when that levee may fail so that we can get people out of the way. That's a big challenge, but it's based on risk management, risk reduction. That's the selling point, not that we're making a smart levee. So with that, I will close. And actually, the Corps of Engineers has approached us kind of with that question. Do you really think this monitoring is going to be workable and useful for us?
Louder, please.
Sorry.
Louder,
Sorry.
please. Sorry.
I usually have a loud voice, people. Very good question. The Corps of Engineers has asked me that question. And in some ways, to be honest with you, I'm still struggling for the right answer. But I think that there are certain things that we go through a reliability study of different sections of the levee and find out the ones that seem to be in worse shape or more present more risk to us, and we focus on those first. And when we see those points, we do develop a model. We know what the design was. We have access to that. So we've got a much easier problem there than the broader one that this research looks at. Basically taking little information and trying to build a predictive model.
Need to go to Professor Sinai first. Yeah.
With the levees you are monitoring, what is the liability that if they fail and you don't predict?
Oh, that's a question I think many of us are going to struggle with as this stuff evolves. My approach is that we do this from a risk-based approach. So we never say something is perfectly safe or will not fail. We say it's a probability, and that gives me some maneuvering room.
Great question. Last question here.
So what are the 2 or 3 main factors or barriers to reduce the cost by factor of 10? And that's a significant reduction you're seeking.
Yes.
What are the biggest hurdles?
We actually have gone through an exercise of assembling all the hardware, and can today put together something that's under $1,000. About the stuff that's off the shelf right now. That's an OEM price. I haven't talked about profits there, but the challenge that's still left is really the signal processing. What that is a less precise GPS receiver. So we give up something, but we gain it on the software processing side, and put more smarts into the system to correct for anomalies and things like that. So the aim is you give up something, get it back with software. And to me, that's a very exciting use because once the software is done, it's profit center.